there is a vector field question on the practice test, and therefore there will be a vector field question on the actual test. They're very tedious and tedious, boring, pick your favorite adjective, but they're useful, right? If you think back to slope fields, and honestly, full disclosure, I've been saying that a lot tonight too. I don't know if it's something that involves disclosing anything. It's just very often Calc 1 teachers will skip over the concept of slope fields. Right? Calc 1, Calc 2. Right? It should be part of a discussion related to solving differential equations by separation of variables. But what happened is in Calc 2, they removed the concepts associated with differential equations. And they said, okay, we're just taking that out of the course. And but what they did was they incorrectly assumed that every form of differential equation should be removed as well. So a lot of folks took out the concept of separation of variables incorrectly. It's foolish because it barely qualifies as a differential equation concept, specific to the course, because it's really just a fundamental aspect of integration. It's one of the reasons why we do things, why we integrate, and to be able to solve equations. Right. So anyway, if you've never seen a slope field, then this looks pretty scary, but it's really not that bad. What a slope field will do is give you a general sense of the slope of a differential equation for any point along any possible differential equation, the solution, which is great, because without solving a differential equation, you could actually get a sense of what type of solution it'll have just by noticing the trends in the slope field. All right, so a very basic one, I'll just show you really quickly. I just do the roughest of sketches. All right, so this is a slope field for an oscillating function. All right, or at least it's trying to be. Right, just by noticing the trend in the slope field, you get an idea of what kind of function is that. It's not going to pinpoint necessarily what the exact equation is of the function, but it'll give you a sense. All right, so maybe this is a sine function, or maybe it's something crazy like the sine, still sine, but like sine of 1 over x. That crazy one that looks kind of like this, and then it goes like a little nuts in the middle, and then it goes on its merry way. It could look something like that too, but the idea is that it's increasing, decreasing, increasing, decreasing, and so on, right? So what a vector field does is really the same concept, same idea, except it's taking that and putting it into, first into the context of vectors, and also allowing for movement in any number of different directions. So a vector field, if you think about movement along a surface, we would be thinking about rates of change as you're navigating up and down, like we're always walking forwards, backwards, left, right, whatever. But if we're in a three-dimensional surface, that could mean that we're going uphill. It could mean that we're going downhill. It could mean that we're going flatways. But that vector would give us a sense of, if I'm thinking in terms of like exertion, how much effort I would have to put into my hike, for example, right? So it's a very basic sense of what it's doing for us, right? So all it's really doing in terms of the mathematics behind it is giving us a plot of all the possible vectors for a vector equation dependent on where you are on the surface, right? Depending on your XY positioning. So if you kind of go back to the surface area graph, like you have, I know it's hard to see, but you have an X and you have a Y. So if you're at some point on the XY graph and you're just moving off in a certain direction, that's going to correspond, so that projects upward to the surface. That's going to correspond using that same movement to some rate of change. That rate of change in this case is going to be some sort of negative rate of change, but it's like in which direction, right? So we have in the X direction, I'm trying to make this look reasonably parallel to X. Or in the Y direction. Right, but that's specific to that single point. Right? What about this point? What about this point? What about that point? What about this point? Like all those other possible points would have all these different vectors associated with it, right? And that vector magnitude and direction as part of a field would give you a sense of what the length of or the amount of strain or exertion that you'd put upon yourself if you're hiking or something along those lines. But it could also be the impact of a gravitational field or magnetic field, any number of different possibilities in each of these directions, right? So a lot of different applications, but it gives you a quick way of understanding the relationship. The drawback though is that it's not quick to do. So once you have the plot, it's very quick to get an idea of what's going on, but it's not quick to create the plot. Unless the components themselves are constant and have a magnitude of 1. If that's the case, oh, then it's great. It's super easy, barely an inconvenience. I mean, you kind of sign up for those cases, right? But then if you see like below that, you have the radial vector fields. Those have components that are both variable. Those take a little while and involve computer-assisted technology or drawing. All right. So what this is telling us, the first one, is we're looking at a vector regardless of position. The vector will be 1, 0. Now, there's no context here, so we don't really know what that means. But if we're talking about hiking, like you have a topographical map, you're looking at it, you're trying to equate that to like physical exertion, you would be saying, okay, so regardless of where I am, the level of exertion is going to be represented by a vector 1, 0, whatever that means, right? So if the X variable represents exertion in your legs and the Y variable represents exertion in your arms, then you would be at a level 1 exertion in your legs and a level 0 exertion in your arms, right, along this hike, no matter where you are in the position, in the extent of the hike or your travels, right? Now, graphically, that's just saying that at every single point, -4, 4, -4, 3, and so on. Every one of these points, you're going to have a vector of 1, 0. I tried my best to say that the wrong way, and fortunately I failed and said it correctly. Get some Mets colors in here. Create some positive vibes. You know, after they get their asses handed to them, 16 to whatever it was, 16 to 4. I shut it off after the 6th inning, so they were only down 10 to 4 at that point. But it's nice to care about them again. All right, so this is what the vector field would look like for 1, 0. All right. So physically drawing it would be a pain unless you're copy pasting like I am. All right. But when you get into the radial vector field, and this is the last thing we'll do tonight. I'm not going to do the whole thing. It takes forever. All right. I'm going to start it off, show you how much of a nightmare it is, then show you how I kind of compromise on this, because I did say that you'd have a vector field on the test. If you looked at the practice test, you'd see that the example that I put there, I believe it was 1, y. So that's my compromise. Having constant components is really easy, a little too easy. Having both parts being variable components, a little too hard. So I kind of split the difference, right? 1 variable, 1 constant. I try to keep it fair. So we have x, y, and let's say, and something else to keep in mind, if you had to do it for every one of these points here, it would just be ridiculous, right? So let's just focus on the points surrounding 0. So just these points. All right, so this is what we call a lattice of points. All right, so this is a lattice of points. Again, if you have experience with slope fields, you're familiar with that term. All right. Although it's probably a while ago, so maybe not as familiar as I'd like to think. All right, so what we do is we list all the x values and the corresponding y values. So each ordered pair, so -1, so there's 9 of them. So -1, -1, -1, 0. I go bottom to top, left to right. That's kind of where my brain takes me. 0, -1, 0, 0, 0, 1, and then 1, -1, 1, 0, 1, 1. All right. So each one of these pairs gives us a vector, right? By definition. Now, you look below, you could see number 4, it's an xy over the sum of the squared values of x and y rooted. So that's saying unit vectors. All right, but what this is saying is that -1, a -1, 1, I have to plot a vector of -1, 1. Or -1, -1. All right. So at -1, -1, I have to plot the vector -1, -1. So what I do is I go to the origin, I draw out -1, -1, and I translate that over the appropriate location and draw an arrowhead on it. Now, there's different schools of thought when it comes to plotting vector fields. One way to do it is to plot it so that the coordinate is the midpoint of the vector. Another way to do it is to find the unit vector for each vector that you determine. so that every vector is every vector is the same size. And what they do is they color code it so that the longer vectors are represented in warmer colors, so like reds, and the shorter vectors are in cooler colors, so like closer to blues and the darker colors. So that's one way to do it, but we're just going to focus on doing it using the actual vectors at the location, because we're only going to do a small lattice of points, so we're not going to go too crazy with it. So, because again, the technology is really where this work gets done. So at -1, 0, I'm plotting -1, 0. So here's -1, 0 in terms of the vector. I'm going to plot it at -1, 0. -1, 1. So -1, 1. Translated so that the endpoint is at -1, 1. And then, you continue the process. 0, -1. So here's 0, -1. Translated so that its endpoint is at 0, -1. 0, 0. That's the 0 vector. So there's nothing in terms of a length to plot there. 0, 1. That's terrible. -1, -1. So you can see it's radiating outward from the center. Some vector fields radiate outward or radiate inward in a circular pattern. Radial, radius, radial, circular. Right. So 1, 0. And then 1, 1. All right. So yeah, we could plot more, but you could already see that even for this quote unquote simple case, there's plenty to put there, in terms of the work to get us to the solution. In order to do it for some of the more complicated ones, I actually had to create a spreadsheet. And, it's pretty nightmarish, right? So what I'll do here is I'm only going to star the ones that you should probably worry about in terms of practice, and these are actually a little bit more challenging than what I would ask you to do on a test, but I'll star the relevant ones. So really, it's just these. All right, with just a lattice of points spanning from -1, 1 to 1, 1. All right, don't go beyond that. If you're doing it by hand, if you're practicing doing it by hand, don't go beyond that, because you're gonna. Well, I just don't want you to hate me. At least not for that reason. All right, so just do that particular lattice of points. But very quickly before I let you go, I'm going to give you another word of the day, and that word of the day is lattice. All right, so you got that one. So you get the second word of the day. But I also want to show you where you can find that applet that I was talking about a little while ago. So resume recording. All right, so if you go into Unit 3, towards the bottom, you see one that says online calculators. I'll be putting another calculator in there within the next couple of days. You'll see it. I'll talk about that. It has to do with spherical coordinates, the one I've been promising you. And I'm still working on it. But if you click on vector field generator, I did not make this one myself. Yeah, look at that link. I probably could have cleaned that up because it's straight up from Wolfram Alpha. So you could see, I mean, more bells and whistles than I'm capable of. So you just type in the squiggly brackets, whatever it is in terms of vector equation that you're looking to find a vector field for. Variable 1 is X, variable 2 is Y, multivariable, so whatever your two, it doesn't have to be in the order that you want, it's just, or the order indicated, just whatever the two variables are. Lower limit and upper limit would be related to the domain of the graph that you want produced. If you only want it to go from -1 to 1, then tell Wolfram Alpha to go from -1 to 1, right? And then it'll compute, well, you'll select compute, and then it'll compute, and it'll give you the vector field, but you can see what it's doing is it's filling in the vector field for the domain that you're giving it. All right, so it's not going to plot something that's precisely the same as what you're going to put on paper, but at least it'll give you a sense that the general trend of your graph is correct. All right, so you can see that there's nothing at 0 because there's a vector with 0 length, and it's radiating outward in a circular fashion. All right, so it gives you a truer sense of what a what the relationship is. If you have experience with magnetism, this should look really familiar to you. All right.
It looks the same actually.
Yeah. So let me stop the recording.